Just as a heads up, I'm gonna be deleting out my backups for last semester's OneNote. So if there's stuff in there that you want to make sure you have access to, I would move it into like a private section of your notebook, like one of the non-shared sections if you want. I don't think it'll affect your connectivity to it, but it might. And I don't want you to lose it if you want it. So greetings. How are you?
I'm good, thank you.
Good. Elvis, it's for you.
What do you mean by backups of Teams? Are those like files that you're storing on the Teams?
No, on OneNote.
Oh, everything on OneNote.
From first semester, I would just move those pages into like a private section, like a non-shared section in your notebook if you want to have access to them in the future. Because I don't know what's going to happen when I delete out. You know what I mean? So anything you want to keep, I'm gonna probably do that on Monday or something. So it's not like it's pressing that you need to do it right this second, but I wanted to make sure I give everybody a heads up. I know this class in particular, with the exam coming, probably still want access to first semester things, particularly if you've been like very OneNote heavy user. So, all right. We're going to set up our new OneNote for the semester. So after you've opened up Microsoft Teams, you should see a 6-hour AP Calc tile on there. Is anybody missing the tile? Okay. Go ahead and click on that tile. In the navigation pane here on the left, go ahead and hit Class Notebook. That'll get the OneNote to populate in here on Teams. Once it's done that, the drop down that says Open in Browser, just pick Open in Desktop App, and we're done those. That should load in and link your OneNote to the shared OneNote that I created for you prior to the start of class, and you should be all set.
I don't have one on the laptop, and it doesn't have the Microsoft Teams for work. It's full downloading, so I'd have to download it again. So can I just do it when I talk to IT?
Absolutely.
Okay.
Yeah, it does not need to be done now, but we're all here, so you know what I mean. I think you can open Teams in web-based and probably go through and do it also. I'm not positive on how you'd get there, but you could try that for a minute or two if you're like so inclined. If you're like, just worry about it later, I understand. It's totally fine. Okay. Anybody other than Jillian on the borrowed computer have any problem? Cool. All right, that's our Teams for the semester. All the class page is going to be set up the same way. So again, like all the download stuff and blah, 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 all there, just like the usual. Okay. All right. Get that out of here. And we're going to kind of get things started. So I have the syllabus in here. The syllabus is the exact same as first semester. The only difference here that I should have updated, there's no exam. These are the AP exams, so just assume that like we've added 5% to the other 3 categories just to even distribution of that. So you would have guessed. Everything else is the same. So the plan for this semester is chapters 5, 6, 7, and 8. Time permitting, we'll look at topics perhaps in 9, 10, and 11. These would be like BC topics. So still like normal calculus topics, but may not be specific to the AP exam only, or the AB exam only, which is what we're taking. Everybody cool? Same setup as last semester. periodically, we're going to go through and kind of do some of the exam questions from first semester. So when I graded your exams, I went and recorded like the points accumulated from each person on every question. So you can see kind of like the questions that we had the most trouble with and the questions we had the least trouble with. So we'll kind of circle back and kind of do some of these things. In particular, though, what we had a hard time with periodically throughout the semester. But I wanted to show you this. And now keep in mind, like, oh no, like, keep in mind, and most people didn't do every question, right? Like, you didn't do all the questions. So am I surprised that some of this stuff at the end is really poor scores on? Probably not, because a lot of us probably didn't get there and do much or even have time to do much by the time we got to those points. But we'll still kind of pick out and go through some of this stuff. The thing I found the most interesting is we start the multi-part questions and like you kind of see a downward slope on each question. Like as they got further into the question, like the performance got worse and worse and worse, which again, not super surprising to me because like the beginning parts were, you know, there was a lot of like just kind of setup-y stuff that I was asking you to do. So we will be looking at exam questions 1 through 6 here as our first set of stuff we'll look through. We're not going to do that today. I did it with first hour yesterday, but with the shortened schedule, we'll kick that can to next week. Where I see you guys 3 times and then twice. Feels like a good time to try to make up that 20 minutes or whatever it would have taken. So we're just going to kind of dive into chapter 5 here, in the start of chapter 5. So your standard first year calculus course is kind of divided into 2 separate halves. You have differential calculus, which is what we did first semester, that focuses on the derivative. And then we have integral calculus, is what the focus will be second semester, where the emphasis is on a new calculus operation called the integral, which will be developing kind of the foundation of that here in chapter 5, much like in chapter 2 we built out the foundations for the derivative. It happens a little bit quicker than the derivative foundation did, mostly because we don't have to do all the limit stuff because we already did it. But that's kind of where we're starting. So as we construct this idea of the integral, which is what these first 2 or 3 sections of chapter 5 are going to be doing, we're going to start with a simpler question. And that question is like, how would I go about calculating the area of a shape like this, where one side of my figure is defined by a function, right? So areas, something we did in geometry even, right? Or even prior to that. What makes this area problem difficult? We have one side that's curved, right? And it's not curved like a circle where it's like a regular curve. It's doing whatever the heck it wants to do there, right? If this is just like a straight line, well, that's fine. It's a trapezoid. I know how to do that. Or if it's a rectangle or a square or whatever, not a big deal. So rather than starting here with like a general function f of x, let's kind of think through this using a specific f of x that's a little bit simpler. We're just going to start with x squared. So we're going to look at calculating this area here in blue. Okay? So if you remember back into like your geometry class, if you wanted to calculate the area of a figure like this, where it's like the basketball key, what did we do? We divided it into like 2 pieces, and we did like area of the rectangle plus like half the area of the circle, right? We're going to kind of take the same approach here. So we can take this figure S and we can just divide it up into a bunch of different regions. And we'll calculate the area of each of these individual regions separately. Everybody feel okay with that? Why did I pick 4 regions to divide this up into? No reason. Just divided it up. What are you noticing about each of these regions, S1, S2, S3, S4 as compared to just S?
Oh, wait, that's compared to S.
Yeah.
Oh, and S is the whole.
S would be the whole thing. Should notice they're looking more like a polygon the smaller we're building these things, right? The smaller we're dividing S up into, the more closely these things will resemble a rectangle or a triangle or a trapezoid or something that's geometric. Everybody's okay with that idea? We can kind of see that from the picture, I hope. Okay. So again, we're still at a problem of, well, we still have a curved side. Now it's less curved than, come on in, than it was before, but it still has this curved side. So what we'll start with is just making an approximation. So what I'm going to do is I'm going to just calculate the area of a rectangle whose base, is just that section of the x-axis that we've divided it. And its height is like this side, where that height now is like some x comma f of x, right? So the height is just going to be f of x there. Everybody agree with that? So if I wanted to do this for the figure that I have here, the area for this first rectangle would be base times the height, which would be 1/4, comma, f of 1/4. So f of 1/4 is my height. What's my function again that I'm using? X squared. So that's just going to be 1/4 squared is my height. Everybody's okay with that? I'll go do my next rectangle. The base is still 1/4. And now the height would be 1/2 squared. And I'll just kind of proceed doing this till I calculate the area of each of these 4 rectangles. So let's go ahead and just compute that value real quick with my calculator. And I'm not going to bother put the times 1 squared here on the last one because it's not really going to do anything. So I have 46,875 is my approximation. Everybody's okay with that? So that's an approximation for the area of S. So did we overestimate the area for S or underestimate? It's an overestimate, right? If I look at the areas for R, each area for these R1, R2, R3, R4 is bigger than the area for S1, S2, S3, S4 because the rectangle overlaps outside above the curve. Everybody agree with that? So here you notice that we're using the right hand endpoint of our interval as our proxy for our height. Why didn't we use the left hand? Well, we could have, right? What if we drew it where the left hand was the height? So notice that here the first rectangle has height 0. Okay. So if we did this, let's see, it's the same thing as this, except I don't have that last piece, right? So 2185. Or 875, excuse me. Was this an overestimate or underestimate? Under. So if I use these two approximations, what can I say about the value for S, the actual value for S? It's in between. Yeah, so yes, Victoria.
So remember that you put in parentheses the height.
Uh-huh.
Well, like, where does this equation come from?
Well, it's just like the area of a rectangle
Oh,
plus the area of the rectangle plus the area of the rectangle plus the area of the rectangle, right? So I'm just doing areas for rectangles.
okay.
So the base is the x-axis and the height is, you know,
And how do you know if it's over or under?
I'm just looking at my picture. Like here, I'm missing a bunch of areas, right? So that area should be, the area that I calculate is less than S. Before, look at all every rectangle is bigger, every rectangle hangs over, so it's an overestimate. Does that feel okay? Alexis.
So you split it up into 4 different rectangles because the answer would be more accurate than doing just one big rectangle?
Exactly. Yeah, and that's exactly what we're going to see next. So suppose we did more rectangles. What do you suspect we're going to do? It's going to be a more accurate answer, right? In fact, now we know we have a better approximation of S. We know it's going to be in between two values that are going to be closer together, right? So what do we have here? So if we're using the right-hand rules, if we use 8 of these, we have like 1/8 times 1/8 squared plus 1/8 times a quarter, da 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 da. 1/8 times 7/8 squared plus 1/8 times 1 squared. And I dotted it in there in the middle. Is everybody okay with me dotted it? You get the idea? All right. Let's see. I'm going to be sneaky here. I'm going to store 1/8 into A. So I can just do like A times A squared plus A times, and then the next one is going to be 1/4 squared. Just do it this way. I don't know why I put a parenthesis there. And then we have 3/8. And then we have 4/8, which is a half. And then we have 5/8, which is 6/25. And we have 6/8, which is 0.75. And then we have 7/8, which is 8/75. And then 1 squared. So there's my overestimate. If I want the underestimate, then it's the same thing except for not the last term. Oops. Do that real quick so I can copy these down. So what we've just accomplished is we got a tighter bound on S, correct? Nico.
So I'm just trying to catch up. So that's the area under the curve.
Yes.
All right. And then what you're doing is multiplying the x by y, right? And just for all those rectangles and adding them up.
Mm-hmm.
And then what's the difference between finding the underestimate and the overestimate? How do you count? What is the calculation difference?
So what we're doing for the underestimates, we used the right hand as our height. So this would be like x comma f of x, where that's going to be my height.
All right.
For the overestimates, we're going to use the right hand endpoint. So that'd be like x comma f of x, where that's my height. So instead of using the left end of my interval as my height, I'm using the right end of my interval as my height.
Okay. So right hand on the overestimate?
Well, we'll get to, it's not always that.
Okay.
But it's in the end, it's not going to matter.
Okay.
So,
Thank you.
yeah, that's what we're about to find here, although it takes a little bit, is that if you do enough of these subdivisions, they're the same, which is where we're going. Is that, you're okay?
Yeah, thank you.
Yep. So the next question, suppose we use infinitely many rectangles. What do you suspect we're going to get? The same for both, which will also be exactly S, right? Yeah, well, that'll be an even better approximation. So what is this going to look like? What's my formula going to look like? Well, the base is going to be 1 over n, because we're looking at from 0 to n, or 0 to 1, and we're going to do infinitely many of these things, so we're just going to have the limit as n goes to infinity. So we're going to just have n of these things. And then the height is going to be 1 over n squared. And then if I'm here, I've done 1 over n and then another 1 over n. So it's going to be 2 over n squared. And at that point, I see the pattern. Okay. And now what we're going to do is we're going to take the limit of that expression as n goes to infinity. Now, to do this, I'm going to do a little bit of rewriting, because the way R is written, not super convenient for me. So what do you notice about each term in this sum? Do you have a greatest common factor for each term? What is it? When I say term, do you know what I mean? So like each one of these things that we're adding up, Is there something in common that I can factor out? It's actually more than that. 1 over n cubed. I have the 1 over n that's out front from the base, and I have the 1 over n squared that's in each of the heights. Everybody see that? So I'm going to do that. And then what's left after I factor that out? One squared plus 2 squared plus dot 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 n minus 1 squared plus n squared. Does that look familiar to anyone? Particularly if you had me second semester for Algebra 2. It's not a factoring thing. It's not a polynomial, it's not a binomial expansion. That's a summation formula. So if you remember when we did sequences in series in Algebra 2, this is the sum of squares. This we had a formula for. Anybody remember the formula? If you do, you're a gigantic nerd because it is a complicated stinking formula, and there's no reason you would have memorized it. So it's n times n plus 1 times 2n plus 1 all over 6. As a quick aside, anyone remember how you would go about getting that formula? Should we talk about that for just a quick second? Feels like a good thing to recap. So the way you'd want to think about this is you have terms and then you have the values. So the first term is just 1 squared. That has a value of 1. The second term is going to be 1 squared plus 2 squared. That's value is 5. The third term is 1 squared plus 2 squared plus 3 squared. That's 14. And then we'd have 30. And then 55. Is that 30's not right, is it? Yeah, that's got to be right. And then 91. So what I'm going to do now is I'm going to look at the values and look for a common difference. So here we added 4, added 9, added 16, added 25, added 36. Those are all different. So we know that it's not a linear relationship. We look at the second common difference. They're all different, so it's not quadratic relationship. We look at the third common difference. Tells us the relationship that we're looking for is cubic. So we'd say, okay, we need a general cubic equation. So I have to solve an equation that has 4 variables in it. I need to create a system of 4 equations. So I'm going to take a term and a value and plug it into here to create a equation. So when I plug x1 in for x and 1 in for y, and then I do the next one, so I'm plugging 2 in for x, and 5 in for y, and then plugging 3 in for x, and 14 in for y, and then 4 in for x, and that will become my system of 4 equations. What's going to be the easiest way to solve a system like this? Fastest way. I heard some whispering, but I didn't understand it. May use a matrix, yeah. So I plug this all into a matrix and then just use RREF on it to grab my coefficients and be done, right? Get in, get out, do it quick. But that's how we'd go about doing that. The coefficients you would get would allow you to factor it to look like this, but that's fine. Everybody cool? All right. So if I want to do then the limit as n approaches infinity, well, let's write it this way. So what would you suppose would be the first step if you wanted to evaluate this limit? Okay, sure. We can do that. That's not a bad idea. If you're not sure what to do, that's probably worth doing. So what do we have there? We have 2n cubed plus 3n squared plus n over 6n cubed. L'Hopital, absolutely. How many times are we going to have to do L'Hopital on this? Yes, excellent. So what Luke said is if we try direct substitution, we have infinity over infinity. That's one of our indeterminate forms. This is a classic L'Hopital problem. If I look at the degree in the numerator and denominator, they're both degree 3. So I know I would use L'Hopital's rule 3 times. So in my numerator, I'm going to have 2 times 3 times 2 times 1. And the denominator, I'm going to have 6 times 3 times 2 times 1. Everything else zeroes out. All I have to worry about are the leading terms, right? Because by the time I take the third derivative of n squared, that's 0, right? So this just simplifies down to 1/3. So if we do the same thing now using the left ends,
Why is the first, like, after the dot, why is the first one n minus 2 times?
because the left end ends, the height is here. So this would be like n over n. This would be n minus 1 over n. The one before that would be n minus 2 over n. Does that feel okay?
Yeah.
Yep, good questions. Now, does any of that make a lick of difference? It's still going to be the sum of squares, right? Still good. That means it's still going to be a cubic relationship. So when we take the limit, guess what's still going to happen? We'd still use L'Hopital 3 times. We're still going to get the exact same thing. Is everybody okay with me just kind of yada-ing that?
So I understand why I understand how we calculate it, but why?
Here's why. Here's why. Okay. So what do we have we can say about S? Well, I know that S is bounded by L and R. And I know the limit as n approaches infinity of L is equal to the limit as n approaches infinity of R, and all that, each of those is still 1/3. What are those two things going to allow me to do? What are those the conditions for? That's the squeeze theorem. What is the squeeze theorem going to tell me then? The limit as n approaches infinity of S is going to equal 1/3. And that is still going to be S, right? If I take S and I just divide it up into infinitely many pieces that are still like exactly the area under the curve, it's just going to be S, right? So what we've done is we've found a way to calculate this area under x or x squared, right? We just build rectangles and we just do infinitely many rectangles. It doesn't matter whether we're using the left end or the right end or some other point in between the interval. It doesn't even matter. You know, whether you're using the midpoint as the height or like some other number as a height, it doesn't matter. As long as that number is inside the interval and you have the evenly spaced, or you have infinitely many intervals, area under the curve. Beautiful. Taylor.
So that 1/3, that's the area.
That's the area of S.
Okay.
Yes.
And is this only for the f of x?
This was specific to f of x equals x squared, the
Okay.
1/3
So it's
part.
not like a general thing, it's specific to that.
Correct. What are we going to do next? We're going to generalize it out so that we can use any graph. Yes, exactly right. So that's exactly where we're going. We did this example to kind of, that was relatively simple, that allowed us to get a feel for what's going on and how this is going to work. Now we want to generalize it so that we can use it in any situation. What's going to be the catch when we generalize this? We may not have a summation rule that we know offhand, right? Us being able to do this using a limit relied on, hey, I know the sum of squares. That was something I did in a previous course. I can do that really easily. We may not have such a nice relationship there to where we can calculate a summation instantly like we did there. Okay. But let's kind of cross that bridge when we come to it. So we're going to apply this generally now. So we're going to have, instead of from the interval 0 to 1, we're going to talk about the interval from A to B. And instead of y equals x squared, we're going to have just any f of x. Everybody okay with that? So we're going to introduce a little bit of notation here to kind of make this a little bit more compact. So we're going to take the width of this interval. That's going to be b minus a. The ending value minus the starting value will give you the total distance of that interval. And we're going to divide it by the number of divisions. So we'll just use n divisions since we know we're going to do infinitely many rectangles at some point. So we're going to call that delta x. The change in x for each rectangle is going to be the width of the interval divided by the number of divisions. Everybody's cool? So that means that the subintervals that we're going to be dividing into are going to be, we're all x naught comma x1. Remember, x naught is just a. And then x1 to x2, x2 to x3, all the way out to xn minus 1 to xn. Remember, xn is going to just be b. So that's going to be the intervals that we're going to be using as our bases. Now, each of those intervals, their length is delta x, right? Everybody's okay with that? So if I want to, I can rewrite each of the endpoints of my, or the right endpoints of my intervals as the starting value plus some number of delta x's. Right? So if each of these lengths is delta x, x2 would be a plus 2 delta x's, which is all we're saying. Everybody's okay with that? What we're trying to do here is just rewrite everything so it's in terms of stuff we're given at the start, right? Delta x just depends on a, b, and n. Now I found a way to rewrite each of my right-hand endpoints as in terms of a, b, and n, which is lovely. Does everybody kind of see why we're doing that? It'll make the formula quite nice when we get to it. Okay. So if I put this together then, hi Anise.
Hi, how are you?
Good, how are you doing? Did you forget it was a mass day?
Yeah.
Yeah, that's kind of what it looked like.
I know.
It's okay.
Happy Three Kings, right? The
Yeah.
Kings. Yeah.
It's the Three Kings Day for sure.
Sorry.
You nailed it. You got that part. All right. So if I go and I calculate, or I write out my formula for r, I'm going to have the height times the base, just like that, right? Using the same technique as before, where f of x1 is my height, and then delta x is my base. For the first rectangle, and then f of x2 is the height, and delta x is the base. That's the second rectangle, and I have that. So again, here's just a picture illustrating this. Yeah, okay, so that's fine. So here again, I can say the area under my region is just going to be the limit as n approaches infinity of the rectangles that are constructed this way. Everybody's okay with that? Again, just bases and heights, right?
Can you like to the area A? Like, of the region?
Oh, area A is the area under the curve.
Oh, that's the whole thing.
The whole thing.
Okay, so when you say of the region S,
That's, yep. The region S is this region.
oh, okay.
And then A is the area
Okay.
of that region. Yeah, I've used S just as an area also interchangeably before, and it's probably sloppy notation on my part.
Oh, that makes sense.
But that's all we're saying. Good questions.
I just, yeah.
Yeah, no. Yeah, totally good answer or question. The notation matters. It's how we communicate. If it's unclear, like ask for clarification, it won't clear it up. It absolutely matters. Yeah. All right. And as we've seen before, I can do the same thing using the left endpoints, right? So instead of starting at x1, I start at x0 because that's the furthest left one. But again, it's still just heights and bases. So instead of ending at the last one, I end with the second to last one because that's the left end of that last interval. Everybody's cool? All right. So notice this in here kind of stinks, right? Like writing that out every time. But all that is a sum, right? So if you remember back to your Algebra 2 class when we talked about sequences in series, we have a handy notation that we can use to represent that sum called sigma notation or summation notation. So that's here. Let me just, there it is. So remember for summation notation, the number on top tells us the end, what the last, how to find the last term in our sum. The bottom, the m tells us how to find the first term. And then the insides here tell us the rule that we use to calculate each of the terms. So for this sum, we do f of x sub m times delta x plus f of x sub m plus 1 times delta x, yada, 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 all the way out to f of x sub n delta x. Is everybody okay with that notation? Do we have to use the summation notation? No, it's the same thing. Should you be able to read a summation notation and be able to sort out what it's saying and like write the expansion so you're able to do something with it? Yeah, I think that's reasonable. But I would never ask specifically to write it as, you know, in this kind of form or whatever. Everybody's cool? All right. I feel like I missed something. Was there something under this? No. Okay. Yeah, okay. Very good. All right, I got a couple of examples here. So let's run through one of these. So it says, let A be the area of the region that lies under the graph of f of x equals e to the negative x between 0 and 2. Using right endpoints, find an expression for A as a limit. Do not evaluate the limit. Okay. Ooh, that's not what I want. So using definition 2 from above, I know that, right? But we can do better than that. Because the thing I don't like is my limit, or the variable of the limit is an n. I don't have an n anywhere in that, right? So what I want to do is I want to rewrite this so that I have some n's running around in here. So I'm going to go back to this summation. And write it that way. So I have the limit of f of x1 delta x plus f of x2 times delta x, yada, 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 plus f of x n minus 1 times delta x, plus f of x n times delta x. Now that's a little bit better, but again, I still don't have this in terms of just n, right? I have these x's and stuff all over the place. So I know delta x is this formula. So that's just going to be 2 over n. I know x1 is a plus delta x, so 0 plus 2 over n. x2 is a plus 2 delta x, so 0 plus 4 over n. And at this point, I have enough of a pattern to where I feel like I can write this out now. So I'm going to have f of 2 over n times 2 over n plus f of 4 over n times 2 over n plus yada, 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 plus f of 2 times n minus 1 over n times 2n plus f of 2n over n times 2 over n. Which I still don't love, which I still think I can do better on, because I can deal with these f's, right? What is the f in this case? E to the negative x. So I'm going to just factor out the 2 over n. And I'd say at this point, you guys would be good to stop. Because now I have an expression in terms of just that. Is everybody okay with this? All right. I feel like I'm going to need some more space there. Part B says estimate the area by taking the sample points to be midpoints and using 4 subintervals and then 10 subintervals. Yuckarooski. So I'm just going to do the first part of it because after you've seen it once, so you don't need to see it again. Right? The difference between doing 4 and 10 is just how annoying can we make it? You know what I mean? All right. So I know then if I'm dividing from 0 to 2 up into 4 subintervals, my 4 subintervals should be these. Everybody agree with that? My delta x is still 2 over n, right? So the first midpoint would be 0.25. The second midpoint would be 0.75. The third would be 1.25. And the fourth midpoint would be 1.75. Everybody agree with that? So my area is approximately, and n is just 4. So I'd have 1/2 times f of 0.25 plus 1/2 times f of 0.75 plus 1/2 times f of 1.25 plus 1/2 times f of 1.75. And now it's just calculator time. I'm probably going to do this systematically. So I'm going to take the 1/2. I'm going to store that to variable a. Oops. So I'm going to have a times, and let's put that in the y equals, I'm going to put in my function. Vars, y vars, function y1. And I'll have a, which is 0, plus my delta x. Then I'm going to add to that the same thing, except I'm going to have 2 a's, 2 delta x's. And I'm going to add to that the same thing, except we need 3 delta x's. Oh, boogers. What am I doing wrong here, guys? I'm using midpoints, right? So 0 plus a is not going to be 0.25. Oops. Get out of here. I just boogered it a little bit on us. It's okay. All right. Do that. So that's what I'll start with. So that's going to definitely start with f of 0.25. Everybody agree? Well, I was doing right endpoints instead of midpoints. Yep. So there's that. And then if I add 1a to it, if I add 1/2 to 0.25, I should be at 0.75, which will be the next one. Ugh. Shoot. Nope, I didn't want to do that either. I forgot to add it. There we go. What the gobbledygook is going on here? There. Sorry. There we go. Then we'll add to that with 2 of these, so that would be 1.25. We'll add to that with 3 of these, so that'd be 1.75, and that's my last one. So 8 56 would be with 4 subintervals using the midpoints. I'm not going to do 10 because that just seems hyper annoying. Do you guys agree? Jack?
How do you tell the calculator? Can you explain one more time what you did with your calculator here?
Yeah, so I wanted to do this plus this, right?
Yeah.
And you could do it manually. There's nothing wrong with doing it manually. I was just trying to do it so I could not have to retype it every single time.
Okay.
So I was just trying to do it in a way where I can just like grab my last thing I typed in and just update one thing and then add it. So I was doing it term by term, adding each of the terms together. And I was just doing it in a way that I could just use my previous script. Yeah.
So I see what you're, okay, I see what you're doing.
If you guys check my Notre Dame, I'll have a couple of homework questions for this section, just like 5 or 6 or something. Nothing's due on Sunday. The 15th will be the first homework set. But don't get behind. Sergio.
Sergio's